Hello and welcome. My name is Waseem Haider, and I'm a tenured associate professor in the School of Engineering and Technology at Central Michigan University. First of all, I would like to thank all the committee members for working so hard and organizing this conference. And my special thanks goes to my colleague and a very good friend of mine, Professor Dr. Khalis Abdul Rahim, for inviting me to this conference. So thank you. So today, the topic of my presentation is recent trends in additive manufacturing. So before I start my presentation, I would like to give you a brief overview about Central Michigan University. So Central Michigan University, as the name states, is present in the state of Michigan, which is right here. And a little star is representing a city of Mount Pleasant, where the Central Michigan University is located. Although there are no mountains, but it's a very pleasant city. So the Central Michigan University has 7 different colleges listed on the left side, and then it offers, these colleges offers a wide variety of programs, from sociology to biology to engineering and computer science, medicine. We do have English literature. We do have a neuroscience. We have over 200 undergraduate and 70 graduate programs. And also, finally, we have a beautiful park-like campus, and we are lucky to have all the 4 seasons in the city of Mount Pleasant. Our spring and summers are beautiful. Our winters are also beautiful, but we do get tons and tons of snow. It's a very pretty and a beautiful and a very walkable campus. So let's start my talk with a basic information about additive manufacturing. So 3D printing is also known as additive manufacturing, is a process of joining materials to make object from 3D models, usually layer upon layer. So a true juxtaposition is that we are adding material bit by bit in contrast to removing bit by bit, especially as you know that in the case of subtractive manufacturing, we remove bit by bit, right, to form a final product. So on the right side, you see a schematic diagram or a flow chart depicting the process of additive manufacturing. The very first step is to create a 3D model in any CAD software. Once the model is generated, then the command is given to the 3D printer, and also the raw material is fed into the printer. Again, with the source of heat, with the selective melting or sintering process at the right parameters, we create a thin layer of a powder. And again, basically the source heat is applied, and then this process continues. Finally, we do get either a fully finished or a semi-finished product. In this slide, it explains the general functioning principle of laser sintering or laser melting. As you could see on the diagram here, that application of a layer of a powder material. So first, very thin layer is created, and then laser basically selectively either melt or sinter that powder. And once that is done, a building platform is slightly lowered, and then the next layer of powder is applied. And again, the laser beam comes, it basically fuses or melts the powder, and then again, the building platform is lowered, and then the process is continued to get the completed product. So additive manufacturing is in fact a game changer in today's manufacturing industry because of a few main reasons. And one of the most important reasons is because additive manufacturing has an ability to form highly complex geometric features almost without exception. Obviously, it is very demand-based and a customized manufacturing, and obviously it's economically viable. So in this graph, I have complexity on x-axis, and I have a cost on y-axis, and then I have 2 lines basically, one representing the conventional method, another representing the 3D printing. So now you could see that as the complexity increases, the cost for the conventional methods or conventional manufacturing methods increases exponentially. However, in the 3D printing, it's kind of a pretty steady, and the cost is not very much, even if the complexity is very high. So again, additive manufacturing is a disruptive technologies because it gives you a design freedom. You can pretty much build whatever you can think about it, right? It gives you a lot of flexibility in terms of manufacturing, and also it enables you to make complex geometries, and also you can really customize the product whatever you want. And once again, it's very economically viable process. So again, if we talk about the major fields of applications in additive manufacturing, almost in all the fields nowadays, additive manufacturing is commonly used, such as aerospace engineering, in automotives, in biomedical, and also in tool and mold making. So according to ASTM, there are 7 classes of additive manufacturing. The first one is vat polymerization, directed energy deposition, binder jetting, material jetting, powder bed fusion, sheet lamination, and material extrusion. I am specifically interested in 2 main processes. The first one is directed energy deposition, and the second one is powder bed fusion. So again, when we talk about specifically the classes, mainly for the metals, I would say that we have 3 main classes. The first one is the laser beam melting, and the second one is the laser melting deposition, and the third one is electron beam melting. So in the first 2 processes, laser beam is used as a heating source, while in the third process, electron beam is used as a heating source. Again, as far as the powder bed fusions are concerned, these are some of the very commonly used printers. So you could see the printers by a 3D Systems, also by SLM Solutions. I've worked closely with SLM Solutions. Similarly, we have a Scandinavian company, EOS. Then we have a Concept Laser printers, and we do have a Renishaw printers. I've been working with Renishaw from past about 5 years or so. I do have their system in my lab as well, and they make pretty cool systems. UK is, by the way, Renishaw is, by the way, a UK-based company. And then we do have SLM 250 by Realizer. So some of these are some of the commonly or commercially used powder bed fusion systems. So one of the most important thing while working with additive manufacturing is the processing parameters. So I have listed few very important processing parameters which one should know when you're doing the 3D printing. The first thing is laser power. Laser power is basically the energy used to melt powder. Secondly, we have the wavelength of that laser source. Another important point is layer thickness. That's the thickness of the process layer. Then we have a scan rate, the speed of the laser movement, how fast your laser is moving. Then we have a spot size, how focused your laser beam is. That's the diameter of the laser beam. Then we have a scanning patterns. It's a scanning strategy used to process layers. So right in the bottom of this slide, you could see the 3 different scanning patterns. There's much more than 3 different, there are many patterns, but I'm only representing here 3 patterns. And you could see there's a chessboard pattern, which is quite cool. And then we have a hatch distance. That's also a very important processing parameter because it gives you a distance between the 2 consecutive layers. And then finally, we have the energy density, which is basically energy per unit volume for additive manufacturing. So some of these processing parameters, needs to be considered when you are printing your part. I'm going to briefly talk about the effect of laser power. So I have the 2 diagrams here. Once you have a high laser power, you could see that the melt pool is much bigger. So once the melt pool is much bigger, which means that it will have a very low cooling rate or very slow cooling rate. Similarly, when you have a low laser power, which means that the melt pool is going to be a small, but that also means that we will have a very high cooling rate. So every time when you choose the laser power, you need to look into, whether you need a very slow cooling rate or a high cooling rate, so on and so forth. Once you have the laser power you select, if you have a slow cooling rate, you could see that you will get a large size grains. And if you have a high cooling rate, you would get a small size grain. As you know, most of you guys know that, the microstructure will ultimately determine the properties of your material, right? So depending on what type of the microstructure you want, so you have to choose laser power in that manner to see if you need a slow cooling rate or a high cooling rate. So you can choose the laser power accordingly. And finally, a little bit in the introduction is that additive manufacturing is also a serial production process, and it is now substituting the conventional manufacturing routes. And it can produce, pretty much all types of, materials, including ceramics, composites, metals, and polymers. And also it can make solid, cellular, or even porous materials, as you could see in the upper example. And in the recent advancements, it is basically we are able to make pretty much all sorts of materials of all of different types. And by the way, this picture is representing Renishaw AM250 system, which we have in our lab. And very quickly about the microstructures of additively manufactured alloys. So I have choose 3 different examples here. The first one is aluminum, silicon, magnesium, and the second one is cobalt, chrome, molybdenum, and the third one is 316L stainless steel. So you could see that, for example, when you focus on cobalt, chrome, molybdenum, you could see that the higher melting point of solutes like chromium or molybdenum result in the formation of grain boundaries. And the immiscible solutes like molybdenum in cobalt chrome is solidified at grain boundaries, mainly at grain boundaries. So, and so on and so forth. So also now, as I said, microstructure really determines the mechanical properties of the materials. So it also depends on, all of these mechanical properties also depend on the build direction. So I have 3 different types of builds. So I have labeled here A series, B series, and C series. So depending on how you build, so this is a regular dog bone shaped tensile testing specimen, and you could see in the little table below that you can get a very high ultimate tensile strength in the A series as compared to B and C series. Similarly, the Young's modulus is very high for C series as compared to A and B series, and so on and so forth. So which basically tells you that your properties, your mechanical properties, are also going to vary depending on your build direction. So now a little bit about my research here is that there is a scarcity of literature when we talk about the electrochemical properties of the materials. So what we are doing is we are studying the electrochemical response of additively manufactured alloys and its difference with the conventional or a wrought counterparts, under different simulated conditions. So in today's presentation, I will be mainly talking on stainless steel and titanium alloys. So here we have 2 types of materials, stainless steel and titanium, additively manufactured, and then as a control sample, we have a wrought stainless steel and a wrought Ti-64. So after we made our samples with additive manufacturing or the ones which we got as a wrought materials, we simply, grinded them, cleaned them ultrasonically, and finally we water rinse them before we start any experiments. So now let's talk one by one, let's talk with 316L stainless steel. So first thing we do is we quickly perform the EDS analysis to see if the compositions are, of the wrought and additively manufactured are same or not. So you could see in the table on the left that additively manufactured and the wrought are pretty much same in the composition. Similarly, when you look at the XRD graph, you could also see that the XRD patterns are pretty much same for both of the stainless steel. But now when we look at the microstructure, you could see a fairly large size grains in the wrought. However, when you look at the additively manufactured sample, you could see a very small cellular types of structures. And then you could also see some directional solidification or more like a columnar type of structure. You do see a melt, melt pool boundaries, and then we do have some remelting regions. However, in some of the regions which I focused as an inset, clearly depicts that there is a cellular pattern was observed during the additively manufacturing. So in other words, the microstructure between the wrought and additively manufactured is completely different. So now moving on to experimental procedures on these two types of samples, we have performed the detailed XPS analysis, which is X-ray photoelectron spectroscopy. Then we have done a detailed electrochemical characterization such as electrochemical impedance and cyclic polarization. By the way, we have used 3 different types of mediums or simulated fluids. The first one is a blood serum, that's a real blood serum, and then we have a simulated phosphate buffer saline and also 0.9 molar NaCl. And as far as the biocompatibility studies were concerned, we have used a pre-osteoblast MC3T3 cell line, and we have taken pictures of these cells on the top of these 2 different types of manufactured 316L stainless steel after 24 and 48 hours. And then we highlighted them, the nuclei and the cytoplasm using NUC blue and actin red. So let's move on to the XPS analysis. So again, it basically tells you the detailed surface chemistry, including if the metals are in the elemental stage or if they are in the oxide forms and so on and so forth. So when we look at the additively manufactured and the wrought oxygen, chromium, and iron high resolution spectras, they are pretty much the same, except that sometimes we do see a little bit of extra oxide formation on additively manufactured samples. Similarly, when we look at electrochemical impedance spectroscopy, you can clearly see that that when you use whatever the medium is, whether it's a blood serum or the PBS or the 0.9 molar NaCl, you could see that semicircle for additively manufactured is bigger than that of the wrought, which basically tells you that it is much more corrosion resistance in these mediums as when you compared it with a wrought. So similarly, when you look at the charge transfer resistance obtained from these graphs, is that you could see that the charge transfer resistance in serum, in PBS, and also in 9 molar NaCl is higher for additively manufactured as compared to wrought counterparts. Similarly, when we look at the cyclic polarization curves, that clearly depicts that if you look at the breakdown potentials, by the way, all the 3 blue curves are for wrought and all the 3 red curves are for additively manufactured samples. And now when these little circles are representing the breakdown potentials, so the breakdown potential for additively manufactured samples in all the 3 mediums is much, much higher as compared to the wrought counterparts. And again, in this histogram is showing the exactly same thing. So finally, as far as the cell proliferation experiments are concerned, again, these are MC3T3 cell line, pre-osteoblast cell lines. So you could see that that the cells are more proliferating. So when you compare first with 24 to 48 hours, you could clearly see that the cells are proliferating, and they seem happy in a sense that they are, their lamellipedia or folopedias are kind of expanding. And at the same time, if you compare the rod and the additively manufactured, you could see that maybe the rod is kind of behaving a little bit better in the first 24 hours, but after 48 hours, you could clearly see that additively manufactured, the cells are much more proliferating for additively manufactured samples. And similarly, on the right, you could see the Western blots we have run for 3 different types. We have osteocalcin, and we have RunX2 and cleavage caspase. So here in each one of them, or at least the first 2 types, you could see that that additively manufacturing is slightly behaving better. However, the rot is a little bit better for the cleavage caspase 3. So now, just to give a conclusion regarding this first project is that the similar chemistry of the passive film was observed for AM and for the ROT 316 stainless steel. And similarly, we have a higher resistance to localized corrosion for additively manufactured as compared to the ROT counterparts in all 3 biological mediums. Similarly, higher cell proliferation, especially after 48 hours, is observed when compared with ROT 316L stainless steel. Now, quickly jumping on to the second project, which is mainly for the dental applications. So we have selected titanium, aluminum, vanadium, and we have printed this one using AM250 Renishaw printer. We have used the laser power of 200 watts, and obviously using the argon atmosphere. We have a hatch distance of 105 microns and a layer thickness of 30 micron. And in this diagram, it kind of tells you that here is that implant, and we have used a potentiostat to run, cyclic potentiodynamic and also the electrochemical impedance, experiments. So before I jump into the results, I quickly want to show you that that using the EDS, we have found the compositions of SLM, or selectively laser melted, and the ROT. They are pretty much the same, and we have used the artificial saliva, and here's a composition of the artificial saliva shown in the upper table on the right. And this artificial saliva has different types of compounds, as you can see, and then their mass concentration is given as well. Now, what we have done is we have divided our, we have made all different types of solutions, because what we did is basically we added let's say a sodium fluoride into the artificial saliva and make a one type of solution. And then we have added, let's say, calcium chloride into artificial saliva and make it as another type of solution. Then we have a, original or pure artificial saliva. We do have a deionized water, and we did use lactic acid and artificial saliva, and also lactic acid and deionized water to see the effect of different compounds on the electrochemical and the other properties of titanium, aluminum, vanadium. So let's first look at the microstructure analysis. So these are the micrographs we got using using the scanning electron microscopy. So you could here clearly see that in the SLM, or selectively laser melted sample, that beta is kind of more elongated. However, the beta in the rod samples are kind of more, not agglomerated, or more agglomerated instead of more like, columnar or longer, right? So this was the basic difference between the microstructural analysis. And then when we did the XRD analysis, we did not find any significant difference, except that we did observe a few extra peaks, mainly at the 2 planes I would like to mention, 102 and 110 planes. We did see strong peaks at those planes in the SLM sample. And by the way, when we did the EDS analysis, the XRD patterns, we did see a little higher percentages of the volume fraction of alpha prime, is a little bit higher for ROT as compared to SLM. So here are the detailed electrochemical impedance spectroscopy data. It's kind of a mix because what we did was, so you could see, for example, in the A graph, you could see that a semicircle was initially lower, but once you go at a little bit higher frequencies, you could see that the semicircle is getting bigger for the additively manufactured sample as compared to the ROT. However, in B and C, you could clearly see that SLM is behaving better in all the frequencies. However, in some other ones, like in D, for example, on the left, you could see that ROT is behaving better. Similarly, when we did the Nyquist plot of SLM and ROT in DI water and DI fluoride and DI calcium chloride and DI lactic acid, you could see that, for example, in DI lactic acid, additively manufactured sample is behaving better as compared to the ROT. However, when you look at a lone DI solution, again, you observe similar type of behavior where additively manufactured curve is behaving better as compared to the ROT material. This is the equivalent circuit models on the right, which we fitted using the EIS data, and we have drawn 3 different models to depict 3 different oxide film behavior. And also we have run the some other experiments, and we got the corrosion current densities, and corrosion current densities of both of the samples are depicted in that diagram on the left. So finally, to conclude that microstructural examination of selectively laser melted Ti-6-4 revealed a relatively fine and higher concentration of beta content as compared to the raw Ti-6-4. And also XRD analysis confirmed that the presence of higher beta phase in SLM Ti-6-4 as compared to ROT. Again, when we talk about the corrosion resistance, we see that selective laser melted has a higher corrosion resistance as compared to the ROT, especially when the pH is above 6. Also, however, when we studied these corrosion resistance in artificial saliva and lactic acid, ROT is behaving, better as compared to SLM, especially when the pH is below 6. And last but not the least, both SLM and ROT depicted significantly reduced corrosion resistance in artificial saliva and lactic acid, and also deionized water plus fluoride solutions as compared to all the solutions studied. So with that being said, thank you very much for listening to my presentation. I would be happy to answer any questions. So if you have any questions, please feel free to write me. My email is listed here on the slide. It is haide1w@cmich.edu. Thank you very much.